A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about plasticity, so let's get started. So in comparison to elastic solids or elastic materials, plastic materials are the materials when they are unloaded after some loading, there is some strain that remains in that material. That is, they are irreversible. That is, they do not return to the same state as they started with before the loading. And the strain that remains is called epsilon with a superscript p, that is called plastic strain. So let us draw our 1D stress strain diagram for materials to understand this concept. So we notice that there is some elastic region for solids, and then there is a region which is called the plastic region. So this region typically is called the plastic region. And when you try to unload a material after loading it inside the plastic region, so let's say you have reached this point, that is this strain, and then you try to unload it, then you don't follow the same line back, but you follow this kind of a line. So we see that there is some strain that remains in the solid. So basically what we're saying is that if you take a ductile material, let's say a wire made up of copper, and you try to bend it, then the wire does not elastically return back to the same position. It stays bent. Or what you notice is that if you try to bend the wire elastically returns slightly, but most of it is plastic deformation that stays. So in the small strain regime, that is, we're still talking about small strains, then there is additive decomposition. That is, the total strain in the body that you notice at any time is a sum of elastic and plastic strains. Now, of course, plastic is something that stays in the body. So the stiffness of the material is primarily only because of the elastic part. That is, the stress that is generated in the material is purely because of the elastic strain. And for this small strain regime, we still assume the linear law between the stress and the corresponding elastic strain. Thermodynamically speaking, what happens is that the plastic strain part is dissipative. So the mechanical work that is done to strain the body, the plastic part is dissipated. It is only the elastic part that can be recovered. So before we get into plasticity, we should understand some variables. And these variables, as we've been talking about, are called internal variables, which are used to track the historical effects in plastic deformations. And this variable that we'll be calling kappa, which earlier we were calling as alpha m's, is called internal variable, or also sometimes called hardening variable, because typically we notice that in plastic materials, as it deforms plastically, the material hardens. And we'll talk about what is the meaning of strain hardening in plasticity. So the kind of hardening we talk about generally in this lecture, and usually also the beginning point of plasticity, is called isotropic hardening. So that is where we assume that there is no directional preference in straining the body in terms of hardening. So if there is some plastic deformation happening in the body, that results in the hardening happening in the body, which is independent of the direction. We'll also talk more about some anisotropic hardening in this lecture towards the end. So let's understand this variable first, because we'll be using that for developing our theories in plasticity. So this internal variable called kappa is basically related to the plastic strain in the body. Now, since strain is a tensor, so we synthesize a scalar out of it, which we call the equivalent plastic strain. So this scalar variable will have information about how much plastic strain has been developed in the body as you deform it plastically. So if you bend a wire and it stays bent, this variable will have the information about how much has the wire bent because of plastic deformation. And we use the idea of the second invariant, actually the J2, that is the second invariant of the deviatoric part of the rate of strain tensor, in this case the plastic part, to synthesize this scalar measure that is called the equivalent plastic strain. So as we discussed earlier, that we have an internal variable, and then we have to specify how the internal variable changes with time. So this is the time derivative or the material derivative of this internal variable kappa. Now, if you want to find out the kappa value or the overall strain because of plastic deformation in the body, because think about a wire, if you deform it multiple times, then the total deformation will be because of all the deformations that have happened. So this is an integral of epsilon p dot from 0 to t. So we are just telling you about the variables which are typically used in developing the theory of plasticity. So the internal variable in plastic deformation which tracks the history of straining is called the equivalent plastic strain, and we'll be calling it kappa in our discussion. Now this was isotropic hardening. Now there are situations where we have anisotropic hardening, and as I said, we'll discuss this later. But in that case, our kappa, that is the equivalent plastic strain, it may depend on additional internal variables as well. Now let's talk about some ideas associated with strain hardening that happens in plastic deformations. The first is that we assume J2 plasticity in this discussion. Now, if you recall the discussion on octahedral shear stress, what we said was that there is a special plane called the octahedral plane, and we measure the shear stress on that plane. And then we use that measure, that is a scalar measure of the shear stress on that special plane, to figure out whether the material will plastically yield or not. And we also showed that J2, that is the second invariant of the deviatoric part of sigma, basically contains the same information as the octahedral shear stress. So it is this plastic yielding that we were talking about that time. So we get a chance to use that now. Of course, there are other models available as well, but in our discussion primarily, and usually in materials such as metals and so on, it is this J2 plasticity model that is used. It is also called the von Mises model or von Mises plasticity model. So basically in this model, you check for the J2 of sigma, which is a scalar measure, and then you check whether that is greater than or less than a certain value to decide what regime are you in. So the yield condition depends on J2, which is the second invariant of the deviatoric stress. Now let's recall that sigma was written as minus P times delta Ij. That's the hydrostatic part or the spherical part. And then you have a tau Ij, also written as Sij. That's the deviatoric part for stress. So in this J2 plasticity assumption or the model, we assume that the hydrostatic part or the stress does not cause flow or plastic flow in the material. It is just the shear or the deviatoric part that causes the distortion or shearing in the body, which ultimately results in flowing in the plastic region. And we have already talked about the equivalent plastic strain, that was this kappa, which is the scalar measure of the accumulated plastic deformation, because we had mentioned that from this integral here. Now, an interesting thing to notice is that epsilon p dot is a positive quantity. So that would mean is that epsilon p will increase monotonically. And that helps us understand the idea that plasticity is accumulated over time. You can't reverse it. The strain because of plasticity, that is the deformation, accumulates over time. Now let's talk about the idea of hardening. What is the meaning of strain hardening in plasticity? So we have talked about the variable kappa, but we haven't talked about what we are going to do with it. So once you find kappa, what you notice is that our yield stress, that is that threshold limit, if my stress that I'm applying on the body crosses that threshold limit, only then the body will plastically deform. So that yield stress is actually a function of kappa. So let's take an example of a ductile wire that you're trying to bend. So if you try to apply some stress on a body to bend it, you will notice that as you keep bending the body over time, after a few cycles of plastic loading, what you would see is that the material starts to harden. And that basically means is that the next time you want to yield it plastically, you will have to apply a larger stress. And in terms of mathematical ideas, we'll be talking about something called a yield surface. And we'll say that as our kappa increases over time, and we saw that it does increase over time because of the third idea of monotonic growth, then the yield surface also expands. So now let's talk about three key ingredients of plastic models. So any study on plasticity starts with an understanding of the yield surface. So to understand what is the meaning of yield surface, first we need to define what space we are working in mathematically speaking. So there's something called a stress space. So this is not our 3D Cartesian space where we have x1, x2, x3 coordinates. It is a space with 6 independent coordinates. So think of the stress tensor. Stress tensor has 9 components, but because of symmetry, it has 6 independent components. So if you were to represent the state of stress as a point, you would require 6-dimensional space. So this space is called a stress space. So if the state of stress changes, that basically means that you move to a different point or a different position in this 6-dimensional stress space. By the way, don't confuse this with the stress plane that we talked about earlier, where we had drawn the Morse circles. Now we also know that because sigma is symmetric and real valued, we can always transform that to its principal coordinate system where we have no shear components, we only have the normal components. So whatever state of stress you have, you can always transform it to its own principal coordinate system and then work with three numbers, which are sigma 1, sigma 2, and sigma 3. Sometimes stress space is talked in terms of a 3D space, which makes it easier for us to visualize things. So this yield surface that we're talking about is a surface in this 3D stress space. Now for a given material, what happens is that there is some region in this stress space where the state of stresses will result only in a pure elastic deformation. So if the stress is very small, then it means that it will be an elastic deformation. And then as you increase your stress, there is a boundary to this region, and this boundary is called the yield surface. So anything beyond this boundary means that the material will plastically deform as a result, and anything on the boundary is called the yield surface. That's the threshold of yielding. Anything inside this yield surface is going to be a safe region, that is elastic deformation. So that's the elastic region we're talking about, and that is inside the yield surface. Now let's say this is our solid and we apply some sort of a shear on the top. What happens is that the solid starts changing its shape because of the elastic deformation. But if the stress crosses this yield value, then what happens is that the solid starts to flow. So the idea is very interesting that the stress state cannot go outside the yield surface. So as soon as you reach the yielding value and you try to increase the stress beyond that, the material starts to flow and equalizes the stress. So you cannot go beyond the yield stress. So we say that beyond yielding, plastic flow occurs and you cannot go to any higher stress. So our stress can either be less than the yielding value or equal to the yielding value, but cannot be more than the yielding value because our material will start flowing and not allow the stress to go beyond the yielding value. And see, practically speaking, it does go beyond the yielding value. But we're talking about a theory, and in this theory that we're talking about, which is a rate independent theory, and we'll talk more about it later today. But as per this first step or the first theory that we're talking about, we cannot cross the yielding stress in the solid body. But as a result of yielding, the body may harden That is, the yield surface now expands. So now whatever stress was causing yielding earlier or was outside the yielding region now gets inside the yielding region, and that becomes an elastic region. So we say that the yield surface starts to expand with deformation. Softening can also happen in some materials. That is, the yield surface shrinks, or the yielding surface can simply translate. And we'll discuss more about it later, but that's a very interesting idea where the whole surface shifts. Now, I've been talking about when the stress crosses a certain value, but stress is a tensor. So just like we talk about J2 of strains, we also talk about J2 of stress. So we compare a tau equivalent, which is the J2 of the tau of the shear stress tensor, with a scalar value, a threshold value, sigma y. And this sigma y is coming from this yield surface model, that is f as a function of sigma comma k. We'll talk more about this yield surface in the next slide. Now, perfectly plastic material means that its yield surface is fixed. There is no hardening or softening happening in the material. And as I've been giving you example of a metal wire, metals are the ones where this theory works best. That is the theory of isotropic hardening, where this yield surface, which is a function of kappa, actually expands with plastic deformation. That is, hardening happens in the material. So the first step in studying plastic materials is that whether our tau equivalent or the stress, whether that is greater than or less than the yield value. So once you identify the yield stress value through the yield surface, then you have to figure out if the material actually is plastically flowing, then how is it flowing? So this is where the flow rule comes into the picture. So we define a plastic potential function G, and through this derivative, we understand the direction in which the plastic strain accumulates. So if you look at this figure again, so basically if you apply a stress in a certain direction, like here, you see that the angle is changing like this. So this helps us understand the direction in which the plastic strain is getting accumulated in the material. So of course it has to depend on sigma, and it also depends on some other properties. And finally, after identifying the yield criteria and also understanding how the material is plastically flowing, now we have to understand the idea of hardening. Because once the material is plastically deformed, it will in most cases harden. So the kappa will change, and then we will go back and identify the new yield surface, and once the loading happens again, we'll identify whether it's crossing the yield value as per the new yield surface, understand the flow phenomena if the yielding is happening, and then update our hardening variables as well. So these are the three key ingredients or steps that are followed in any plasticity study. Now we'll go in steps to understand the three key ingredients in a bit more detail. So first, we'll talk about isotropic hardening. That is the J2 model, where we study the J2 of stress to identify whether the yielding is happening or not. As we said that the deviatoric part, which is given as S or tau, is the stress tensor minus its isotropic part, and J2 is simply the second invariant of the deviatoric part, and this yield surface, which is a function f equal to 0, and f is a function of sigma, of course, and kappa. So the first model we talk about is the von Mises model, and this model basically is simply saying that this square root 3 times j2, which is related to our tau equivalent, equal to our sigma yield value, which is the function of kappa. So f is given as the tau equivalent minus sigma equal to 0. So when tau equivalent becomes equal to sigma, that's the meaning of the yield surface. If tau equivalent is less than sigma yield, that's elastic region, and tau equivalent cannot be greater than sigma yield, because as soon as it reaches the sigma yield value, it cannot cross it, the material starts to plastically flow. So this model is typically used for ductile metals like metal wires, and we notice that it is only the tau that matters here, not the hydrostatic pressure. So these are pressure independent models where the plastic deformation or flow happens purely because of the deviatoric or the shear part. And the surface in our three-dimensional principal stress space that we just talked about earlier looks like a cylinder, but if you try to draw it in a pi plane, it looks like a circle. So pi plane is also called deviatoric plane. We know that SII is a 0. That basically means that if we are talking about a sigma in this plane, then sigma 1 plus sigma 2 plus sigma 3 is a 0. And this actually is a plane because sigma 1, sigma 2 and sigma 3 are the three axes in the 3D stress space. So this is that x plus y plus z equals 0 plane that passes through the origin. So this is the same as the deviatoric plane in our 3D stress space, and it's called the pi plane. So whatever points exist in this plane are basically denoting states of stress, which are all deviatoric stresses. And since in this model we compare the deviatoric stress, so the yield surface can be drawn in this plane, in the deviatoric plane, and this yield surface becomes a circle from this von Mises model. Now actually in this 3D stress space, if you look at the line, which is the line where sigma 1 equal to sigma 2 equal to sigma 3, this plane that we're talking about, the deviatoric plane, is perpendicular to this line. And this line actually is called the hydrostatic axis, because any point on this line is basically a spherical state of stress, because all three principal values are the same. So the deviatoric plane has to be perpendicular to this line. And remember, the reason we can work in this deviatoric plane for discussing yielding is because we assume that for these materials like metals, and that's true, that yielding does not depend on the hydrostatic pressure. If it did depend on the hydrostatic pressure, then we cannot work in this plane because this plane has no information about the spherical part of the stress. The other common yielding criteria or the pressure independent model that we use is called the Tresca model. And if you recall, this max of these three is basically for these three more circles, it was this top point that is a maximum shear stress in the material. So this is basically saying that it's a maximum shear stress that is used for checking for yielding in the body. This model is related to the von Mises model, but it's a little conservative. That is, it predicts yielding a little earlier than the von Mises model. And in the pi plane, it is denoted by a hexagon. So the yielding surface for the Tresca model is a hexagon, not a circle like von Mises. And then another popular model, but this model is a model for pressure sensitive materials like soils, rocks, or granular materials, is called the Drucker-Prager model. And as you can see that the yield function f, the yield surface, in this case also depends on the pressure value. Now think of some granular materials, let's say soil. So if you take a cube of soil like this and you apply some shear stress on the top, then you will see that the cube of soil will shear, or if you think of the cube as just one material, you will see the material to be plastically flowing. Now, if you increase the pressure, you have an intuition that the friction increases. So now you will need more shear stress to let the grains move over each other. That is, if you think of the material as a whole, for the material to plastically flow. So these are called pressure sensitive materials, where the yield surface depends on pressure. So as we said, that once we understand the yield surface, the yield criteria, now the next thing is to study the flow rules. So this plastic potential function G, which is also a function of sigma and kappa, helps us understand what is the value for this material derivative of the plastic strain tensor. By the way, lambda dot is greater than or equal to 0 in this case. So for incompressible materials, we use the associated flow model, where our plastic potential function comes out to be the same as F, that is the yield function that we've been talking about in the yield surface. Whereas for non-associated flow, G is not the same as F, and this is more common for soils or granular materials where the volume can change. So the choice of our G function here will also help us control dilatancy, that is, help us identify how much volume change will accompany the plastic flow in the body. Now, this is an idea of consistency that basically says that if you are on the yield surface, that is F equal to 0, and since we also know that you cannot cross the yield surface, so if you're moving, then the only way you can move is you can move on the yield surface during plastic deformation. So F dot, that is the change in the F value with time, has to be 0 if you're on the surface, and that will usually help us determine the lambda dot value. So the main takeaway from this slide is that there are associated flow models or rules and non-associated flow rules, and the major difference between them is whether the material is incompressible like in metals, or whether the material volume can change along with plastic flow, that is more common for granular materials like soil. So the third step is to identify how the hardening happens or how the yield surface changes. So we talked about the yield function for J2 plasticity like this. So in this theory of isotropic hardening, we say that the yield sigma, which is a function of kappa, is basically some initial yield, that was the yielding when there was no hardening, that's the first time you plastically deformed the material, plus kappa times some hardening modulus. So it's a linear model for the yield stress as a function of kappa. So as kappa increases over time, and you know it does, sigma yield increases linearly with that. So you insert this function into your yield function to get the updated yield surface. Now we talked about the idea of kinematic hardening, that is anisotropic hardening. So let's explain something called Boschinger effect, and this will help us understand the idea of anisotropic hardening. So let's say you take a metallic bar and stretch it so that it plastically deforms under tension. And what you notice is that when you unload it after it has plastically deformed, and now you apply compression on it instead of tension, then what you notice is that it yields much earlier in compression as it did earlier in compression. So because of the plastic deformation happened on the material during tension loading, the compression yield stress has reduced. And this is called Boschinger effect, where what we are seeing is that it has a directional preference now. Compression is yielding much earlier than tension. So it's like the material has hardened in tension but softened in compression. So if you think in terms of yield surface, if you were here earlier and if you had the limit for yield stress for tension and compression, now what's happened is that this value has reached here, but this has reached here and it has softened. So it's like the whole surface has translated from the blue region to the green region. So this is what we meant by saying that the yield surface can translate in kinematic hardening. So this has to be dealt differently. Now, whatever plasticity models we have discussed till now were rate independent in the sense that there was no explicit strain rate dependence in our models. Of course, our models took care of the historical effects and loading path, but there was no effect on how fast the overall strain in the material is changing, whether you are straining the material very quickly or slowly. Also, till now, in the rate independent plasticity we discussed, there was a very sharp yield surface. That is, we suddenly went from an elastic region to a plastic region. But realistically, and particularly for some materials which follow the viscoplasticity regime, there is a smooth transition between elastic region and plastic region. So the yield surface is hazy, so to say, and plastic flow is controlled through an overstress. So earlier we said that we cannot cross the yield surface. But in this viscoplastic model, we say that we can go or take our stress beyond the yielding values, and depending on how much of an overstress we are applying, the rate at which the material deforms plastically will be different. So how fast will plastic flow happen is something that can be explained with these models. And also, for some numerical reasons which are beyond the scope of this course, viscoplastic models bring in some stability to those numerical algorithms as well. So we'll not discuss any equations in this viscoplastic models, which is also called rate dependent plasticity. I'll just discuss the overall essence of these models. So typically we see that for soils and polymers and metals at high temperature, they show rate sensitivity, that is the plastic yielding and plastic flow. They depend not just on the state of stress, but also on the rate of loading. So the ideas such as creep and relaxation effects, which become important for viscoplastic materials, can be captured using this viscoplastic models. So there are two common models. So in the first Perzeno overstress model, we assume or allow overstress. That is, you can apply a stress which is outside the yield surface. So you're allowed to go outside the yield surface, and depending on how much of an overstress you have applied, if you have a very large overstress, it's like a large potential that you apply that results in a faster plastic flow. And the second approach, what you do is that you still go beyond the admissible yield surface, that is, you apply an overstress, but then what happens is you allow the stress slowly relaxes to the yield surface. Now, some advanced ideas such as in damage. So it happens that when you load the body repetitively, let's say, there are some micro cracks or voids or defects that develop because of this fatigue, and this can be captured using a damage variable d. Now this variable lies between 0 and 1. So d equal to 0 means it is undamaged, and d equal to 1 means completely damaged material. Now of course this d can also be a tensor to take care of the directional nature of the damage that has happened. So the way we couple the effect of damage into plasticity is through this equation, where earlier, remember, we were saying that sigma, the stiffness that is generated in a material, is purely because of elastic strain, but now you multiply a 1 minus d with that as well. So for a purely new spring, the spring will be very stiff. That is, for the same strain, it may require a large stress to generate that. So it will resist deformation. But as the spring gets older, D increases, then it becomes softer. That is, with the same strain, it will resist that straining less and the stress generated will be less. So, a lower stiffness because of damage. Now, in these advanced ideas, there's also another interesting model that is used for granular materials which are flowing. So, the constitutive law that we use is something like this, where our tau, that is the deviatoric part of the stress tensor, the response, depends on the rate of deformation tensor D, like we had in fluids, but there's also an effect of pressure. So firstly, if there's no pressure being applied to the material, then there is no shear stress. That's very much valid for a cube full of granular material. If you don't apply any pressure, there's no friction between the grains and therefore there's no resistance to any rate of deformation. There's no shear stress required to create deformation as such. But since it is a fluid-like model, there's also a viscosity in addition to this scalar measure called the effective shear stress. But let's look at this viscosity here. So this viscosity is modeled like this, where it depends on something called an inertial number I. So when this I is close to 0, then what happens is, if you look at the viscosity here, then mu becomes equal to mu s. That's like a static friction. So that's like a solid-like regime where the grains may be jammed. And when this I tends to infinity, which would happen if our gamma dot is very large, or if our pressure was really small, then the mu would actually tend to mu2, which is the other end of the spectrum for dynamic friction. So this model, which has a dependence of the viscosity, the fluid viscosity, on the inertial number, helps us model granular flows which can range from a very dense solid-like behavior to a fluid-like behavior. So the interesting part is that this mu-I rheology model for granular materials is rate dependent, whereas its counterpart, the Drucker-Prager model, was rate independent. However, both these models incorporate the effect of confining pressure. So before closing the lecture, please have a look at these concept check problems. So finally, we summarize this lecture on the constitutive modeling for the plastic regime. So the main takeaway from this discussion is that there's a yielding which defines the onset of plastic deformation. There's a flow model which helps us understand the direction of plastic flow. And then there's a hardening which results because of plastic flow, and that has to be incorporated back into the yield surface modification. There are rate independent models versus rate dependent or viscoplastic models. There are advanced models available as well that take care of damage and confining pressure rheologies. The constitutive modeling in general requires a lot of microstructural study. So one has to study what's happening at the scale of microstructures to understand how the stress and strain are related, or the stress and strain rate are related. A lot of experiments have to be performed, and these new models have to be tested using numerical simulations to see whether they generate similar effects as seen in experiments. So this brings us to the end of lectures on constitutive modeling.